All right, so we talked about absolute zero, right, which is a pretty cool thing. And we just want to kind of remind ourselves about what absolute zero means and how temperature relates to motion. Our ability to measure temperature is usually through a thermometer. And when we talk about a thermometer, what that means is it's usually a column of some liquid. So here's the liquid inside here. And just like we described our barometer before, where we had mercury, and that's what used to be in thermometers as well, this column of liquid responds to the collisions on the outside of the glass, and that's why that little thing down there was usually, the little ball of mercury would usually break relatively easy, because this needs to be relatively thin so that the temperature can kind of penetrate it a little bit. But then the movement there would cause pressure to increase, and then the mercury would move up in our column, and that's how our thermometers work, right? So measuring that change in mercury is related to temperature. So temperature, again, is related to motion. Okay, so what happens to gas pressure when you raise the temperature? All right. What happens to gas pressure when you raise the temperature? And now I have two different scenarios where we want to kind of think about that. If the container can expand in response to the force, how will the pressure change? Well, there will be no change in pressure. What you'll have is a change in volume. And that volume is occurring because as the pressure increased, the volume changed, right? In a rigid wall container, if we increase the temperature, then the pressure inside that vessel will increase drastically if the volume can't expand. All right? So this, a lot of our kind of conversations that we've had so far have been about balloons. And balloons, we kind of think of them as elastically changing to whatever shape the pressure requires. But we have to also recognize that any of these changes in temperature, changes in pressure, right, can occur in rigid walled containers. And so in those types of scenarios, you have changes, but no changes in volume, right? Okay, so what happens to gas pressure when you increase the number of moles of gas in the container, or the number of molecules of gas in the container? So if the container can expand and I put more moles into it, what's going to happen, Fred?
Let's see. Can expand is like a balloon, right?
That's right.
So if you put more into it, it's going to get bigger, right?
That's right. But the pressure won't change, right?
Oh, okay, yeah. The balloon's going to get bigger, but because of the pressure's trying to change, right?
Yeah, the pressure, there was a need to increase the pressure, but because the container could expand, the pressure doesn't change, just gets bigger. But in a rigid wall container, then our pressure will increase because more molecules are there hitting the walls, but the molecules can't cause the chamber or the container to actually expand in volume. Okay, which of the following is likely true about a balloon taken underwater?
Oh, I know this. The balloon, let's see, the balloon compresses. The balloon is compressed.
That's right. Now, what's causing that compression?
Oh, the molecules on the outside of the balloon are pushing on the balloon and making it shrink. The pressure on the outside is greater than the inside.
That's right. Very good. All right. Another relationship. Now, so far we've talked about two laws, a relationship between pressure and volume, and a relationship between temperature and volume. And now we're going to talk about a relationship between pressure and temperature. Pressure and temperature. Now, let's just review these really quickly. What is the relationship between volume and pressure? Is that a directly proportional relationship or an indirectly proportional?
I can't remember what those mean.
Directly proportional means that as one goes up, the other goes up too. And you can kind of sneak in there an equal sign, just to think about it that way. If they're directly proportional, as the pressure of a container, of a balloon, for example, of a gas goes up, then the volume goes up. The pressure on the outside of the balloon, right?
But that's not right, is it?
That's right. That's not right. As the pressure increases, what happens?
The volume decreases.
That's right, the volume decreases. And so it's not an equal sign like that. It needs to be like this, where, and again, these aren't equal sign because these are different units, but it's an indirectly proportional relationship. All right? Now, what about pressure and temperature? Pressure and, volume and temperature? Volume and temperature, that was the previous law we went over.
Let's see, volume and temperature.
Are they equal, or is it inversely proportional?
Let's see, we said that if you heated the temperature, the volume of the gas, well, let's see, you put the balloon in the fridge and it got small.
That's right. So we decreased the temperature, and what did the volume do?
It went down too, it's decreased. So it's directly proportional.
That's right. And again, we should use these kinds of relationship here because it's not, volumes are in units of milliliters or liters. Temperature is in unit of Kelvin, Celsius, Fahrenheit, something like that, right?
Okay.
Now, that being said, when we're talking about temperature now, you have to always use Kelvin when we talk about these temperature relationships. And that's because it gives us one good linear relationship between 0 Kelvin, so if this is where our 0 Kelvin is, up to whatever value we want to, all right? And because Kelvin, again, identified that an absolute 0 existed, the scale for Kelvin goes from 0, all positive. You never have negative Kelvin. But Celsius and Fahrenheit, they use different parameters to kind of make their thermometers. Celsius and Fahrenheit were thermometer makers, right? They were good at blowing glass, and so they made thermometers. Kelvin was not a thermometer maker. He worked on temperature and looking at gas and volume, or temperature and volume relationships. And that's how he identified, theoretically, the absolute 0, which later showed to be the case. All right, so moving on to, those were reviews, moving on now to pressure and temperature. Pressure and temperature are directly proportional, or in other words, if I take a container that's fixed volume, right? Now, you have to see that when we're talking about pressure and temperature, we can't let the volume change as well, because if the volume's changing, then the pressure won't build up if you change the temperature, right? Just like we were talking about before, volume and pressure, if the volume changes under different pressure conditions, we have to take out the temperature factor. It has to be the same. Volume and temperature, same thing. If the volume and temperature shift, then that is always under an assumption that the pressure is fixed. If we're just talking about these two parameters, all right? And same with Gay-Lussac's law here of pressure and temperature. That means the volume of the gas is fixed. So if we have a fixed volume of gas and we change its temperature, then increase the temperature up, the pressure will increase as well, directly proportional. And I found this out as a young boy. My job was to burn the garbage sometimes, and I would put the garbage into the big can and light it on fire, and it was a lot of fun. I got to play with fire, got to see stuff burn. But I always knew that if you put the bathroom garbage into the fire, oftentimes there'd be an explosion. And I didn't know what was going on. I never figured it out. Until gradually, later on, I thought about it. I realized it was these cans, either shaving cream cans or hairspray cans, cans that were under pressure, fixed volume. And so when they got hot, they pressurized and then they would explode. All right. So We can combine all these parameters, just like we showed early on, that we could combine the relationship between pressure and volume, like that. We can combine all of these into what we call the combined gas law. And now have the ability to say, let's say I have a given pressure, or gas at a given pressure, fixed or given volume and given temperature, and I change pressure and volume, I can tell you what the new temperature is. Or if I have the initial pressure, volume, and temperature, and I find out the new pressure and temperature, I can tell you what the new volume is, right? Using this relationship. Okay, this combined gas law. Now, this combined gas law works for what we call ideal gases. Ideal gases. Now, in reality, no gas is ideal, but most gases behave ideal enough for our types of calculations and problems that we're going to answer. Real gases, when they come close and collide, there's actually always a little bit of stickiness or a little bit of influence that they have on each other, not just a complete elastic collision. And there are corrections for that, and we won't go into them, but they are around. We'll show them to you briefly at the end. But we want to recognize that there is a difference between ideal and real gases. Okay, so if we had a situation where we knew the volume, 22.4 liters, and we knew the temperature, 25 degrees Celsius, and we heated it to 200 degrees Celsius, what would be the best way to find the new volume?
So you got 22.4 liters. You're heating it from 25 to 200. So you want to deal with volume and temperature, right? Let's see, which one of those? That's B, right? Volume and temperature?
That's right. Very good. So that's how you do that, right? You identify the initial volume, initial temperature, new temperature, and if they're asking for the new volume, you can find out what it is. Okay? Now remember, for temperature, you always want to convert temperature to Kelvin to make this work, right? And how do we convert degrees Celsius to Kelvin? Do you know?
I think I do. Did we do this a while back?
Yeah, we did it a long time ago, but I don't think very many people remember.
Isn't it like 273?
That's right, 273. Now, what do you do with the Celsius to convert it to Kelvin? Do you subtract that 273 or add 273?
Well, that's a good question. I can't remember.
So let's use an example. 100 degrees Celsius. Do you subtract the 273 to go to Kelvin, or do you add the 273?
I guess you have to add it because you said that Kelvin's never less than 0.
That's good. That's good. That's perfect. That's exactly what we need to do. We need to realize that Kelvin can never be negative. So if I'm going from a value, I can just think of a hypothetical value to Kelvin, I'm going to need to add the 273. All right, 373 Kelvin will be equal to 100 degrees Celsius. Very good. And going from Kelvin to Celsius, we would just be subtracting the 273. Okay. Which units must always be used in all gas law calculations?
Well, we know, I don't know, can you use different pressures?
Yeah, you can use different pressures. So atmospheres is not the answer. You can use torr or millimeters of mercury. What about liters? I mean, who would care if we expressed it in milliliters, right? That's no big deal.
Oh, Kelvin. You have to always use Kelvin.
That's right. When we're using temperature, we don't want to use Celsius or Fahrenheit. We have to use Kelvin because that gives us our 0 positive value, never a negative value. Good. All right. So our combined gas law. Let's see if we can use our combined gas law to answer this question for ourselves. All right. You guys work on this. Push pause, try to get the answer, and then Fred and I will work on it. All right, what do you think, Fred?
Well, that's the combined gas law. Pressure, volume, temperature. It says that it occupies 500 milliliters. That's the volume, right?
That's right. So the initial volume is 500.
And the initial pressure is, what's STP? Well, it says down there STP is 1 atmosphere. So it's 1, right?
Very good. 1.
And 273 is the initial temperature.
Very good. 273. That's standard temperature and pressure. Whoops. That's not supposed to be a decimal point there. Standard temperature and pressure.
Okay, and then it goes to 85 degrees Celsius.
All right, 85 degrees Celsius. So I put 85 down here for the new temperature?
I think so, right?
No, we don't. Why not? Why don't we put 85?
Oh, yeah, because it has to be in Kelvin.
That's right. So 273 plus 85, right? So we're going to put in there 358. What's our new pressure?
560 torr. How does that relate to atmospheres?
Well, I know that I could change this. I know that 1 atmosphere is 760 torr. Is that all right?
Okay, all right.
So 560 torr. Then what?
Well, then you just got to solve for the volume.
That's right. So the volume is here left over. So, calculator, 760 times 500 divided by 273 times the 358, move that over here, divided by the 560. So 889, and that's volume. So it went from 500 milliliters to 889 milliliters. And that makes sense because we heated it up. We decreased the pressure, right? Okay, very good. So that is our combined gas law. Okay, good place to stop. Excellent job, Fred.
Thank you very much.